Hello everybody, this is Mr. Walters, and we're going to solve a gravimetric analysis problem that was similar to a problem that we did in class from Chapter 4. So this is reactions in aqueous solutions, and we're going to do this analytical technique which utilizes several of the principles that we've talked about in class, including basic precipitation reactions and analysis. So let's read the question. We've got an unknown ionic compound. We'll call that XBr. It contains bromide ions and has a mass of 0.161. That's in grams. This compound is added to 500 mils of distilled water. Suppose 0.20 moles of silver nitrate aqueous is added to the solution. We're going to add this in excess. A solid precipitate is formed, and that solid precipitate is silver bromide AgBr. The precipitate is filtered, dried, and measured with a mass of 0.3482 grams. The pH of this solution is 6.8. Use the above information and what you know about electrolytes and the chemical principles to answer the following questions. So, let's take a look at what's going on here. First question, write the net ionic for the precipitation reaction which occurs in the above example. Here is our ionic solid. We're not quite sure what this X is, but it's a metal. Could be sodium, potassium, lithium. It could even be an alkaline earth metal with a double positive charge. We're just not sure. We do know that the mass of this unknown bromide sample. Well, we're going to put this into the distilled water, and this is going to ionize to X positive plus Br minus. Both of these will be hydrated with water molecules, and of course that means aqueous. We have 500.0 mils total volume, or final volume at this point. Well, we want to know the precipitation reaction, so we've added, if you read, we add excess amounts of silver nitrate aqueous. And again, this is in excess. So I'm going to put excess here. Now, when we add this silver nitrate to this solution, what's going to happen is the silver ions are going to collide with the bromide ions, and according to the solubility rules, we'll get a solid precipitate, silver bromide solid. And that silver bromide solid is going to settle down here at the bottom of the beaker. So that's AgBr solid is going to be produced. So here, this is the net ionic for the reaction. Again, we've got the silver nitrate being added. It's releasing numerous silver ions, and don't forget that nitrate ions are also going to be present, so let's make a note of those. The net ionic, again, let's rewrite it here, is Ag aqueous plus Br minus aqueous yields AgBr solid, and there's our net ionic. Well, remember the silver is in excess. So there's going to be silver left over. After all this solid is produced, we're still going to have silver ions left over. The bromide ions, for all practical purposes, are now going to be bound up as the silver bromide. So let's eliminate these Br minuses. They're gone for all practical purposes. And let's remember that the ions that we have present now are these excess silver ions. We've got plenty of solid precipitate, which is represented here. It's more dense than water, it goes down to the bottom. We also have this original metal ion, so we're not sure what that is, but we'll call it X positive. The Br minus, again, is consumed in this reaction and is present now as that solid, so that's why we're eliminating this. Don't forget we have nitrate, which is a spectator ion in this reaction. So let's look at the next question. And what do you know? That's asking about nitrate ion. Is nitrate involved in the above precipitation reaction, yes or no? The answer there is no. It is a spectator ion. Let's move on to the next question. After the reaction is complete, state all ions present in the remaining solution. Would the solution conduct electricity? Well, let's take a look. Notice we have nitrates present. We have X positive ion. We have Ag positive ion. Now remember, this is an aqueous solution, and if you recall, the pH of this solution from the original question is 6.8. That looks better. So, in this solution, we have small amounts of H positive. So I'm going to put H positive in here. Notice it's slightly acidic. And again, I drew this small because it is small amounts relative to the large amounts of nitrate and the large amount of the silver ions and the X positive ions. There is also small amounts, very small amounts of hydroxide ions. So these are present. There'll be a little bit more H positive compared to the hydroxides at that particular pH. So, definitely going to conduct electricity, and we can write these out now. NO3 minus, Ag positive, that's present because we were in excess amounts of silver nitrate. But of course, we also have X positive. We also have small amounts of hydroxide and small amounts of H positive ions. Let's see what else we have. What's the pOH of the solution? So we know that pH plus pOH equals 14. So pH equals 6.8 and pOH equals 7.2. So I've cleaned up this solution a little bit, and here's what we have after the reaction occurs. We've got the silver bromide solid. Now remember, in the question we do know the mass of this after it's filtered, after it's dried. The mass is given as 0.3482 grams. And let's write down, so that's the mass of the precipitate. Remember the original mass of the XBr, let's just write this up here just so it's handy. So the original mass of that solid, obviously before we dissolved it in solution, was 0.161 grams. But anyway, let's get back to this solution so we get a handle on what's going on. Obviously, it's a strong electrolyte solution. Look at the negatives and positives. Again, since the pH is 6.8, we have small amounts of hydrogen ions, just small amounts because the pH is 6.8. It's only slightly acidic. The concentration of these hydrogen ions is small, but it is a little bit more than the OH minus. Now, these ions here are hydrated. They're surrounded by the famously polar water molecules. So if we're going to look at one of these, and again, these silver ions are spread out evenly in this solution. The nitrates are spread out, and all of them are hydrated by many water molecules. But just looking at the silver ion, the water, which is polar, has a partially negative oxygen and two partially positive hydrogen tails. So if we do a shorthand version of the water, we can kind of get an idea of what it means when we say aqueous. Aqueous is when these ions are hydrated by these water. And notice the orientation of the water molecules. The point of the water molecules, that represents the oxygen, which is partially negative, and then two partially positive hydrogen tails. So these water molecules are really gathered around this ion. And we have that intermolecular attraction going on between this polar water and this aqueous silver cation, positively charged cation. So there it is. So again, that's what we mean by aqueous. They're all hydrated here by these water molecules. Of course, if you have a negative charge, the waters are spun around in the opposite direction, so that's important. Also, what I want to mention is I'm not showing the solvent in here. There is more water in here than any of these other ions, much more water. So if I ask for the most abundant species in the entirety of this solution here, you'd say water, because there's more water than any of these other aqueous ions. So let's get back to the question. We've got 500 mils, final volume here. We do have the mass here. We'll get to that in a second. We have the mass of the original XBR. Well, it says determine the concentration of the nitrate ions in moles per liter. So pretty straightforward. Big M, molarity, is moles of solute, and in this case we want moles of nitrate ions divided by liters of solution. That's final solution, and that's my final volume here. So notice I need liters, so that's going to be 0.5000 liters of total solution. So all I need to do is find the moles of the nitrate that we added. Well, if we go back up to the question, let's see if we can find that. Okay. So here we have 0.20 moles of silver nitrate, that's aqueous, is added to the solution. So there's our number of moles. Let's look at the ionization of silver nitrate. We know that silver nitrate, if you have silver nitrate, just going through this methodically, if you had this in water and you go from, let's say that we had the solid form, the solid salt of this, and if you put it in water, let's look at the ionization. It ionizes in a 1-to-1 ratio. So notice 1-to-1-to-1. So if we add 0.2, not to insult anybody's intelligence, but just a reminder, this 1-to-1, it's going to be different. If this is 2-to-1 or 3-to-1, it's going to be different. But if you have 0.20 moles, it will ionize and produce, yes, of course, 0.20 moles of Ag positive and 0.20 moles of nitrate. Again, we're following this 1-to-1-to-1 ratio. If this were 1-to-3, you'd have 0.2 going to 0.6. That's important. But as it stands, we can go down here and we simply plug in 0.20 moles. So this is not meant to be too complex, but you just got to get it down. And then we can do the math, and we'll end up with 0.40 moles per liter, which equals big M. Let's look at sig figs. Notice just because I converted this to liters, I don't lose sig figs. I have, this is 1, 2, 3, 4 sig figs here. So that's still 4 sig figs. I don't lose sig figs when I convert. We had some people just putting 0.5 here. There's no losing of sig figs just by converting milliliters to liters. So there we go.